Hello and welcome. My name is Nick Brimley and I'm the Marketing Director for the Slag Cement Association. I will be moderating today's webinar, The Role of Slag Cement in Creating Sulfate-Resistant Concrete. Our speaker today is Keith Maddrey. Keith is a technical services engineer for Argos and has over 30 years of experience in the cement and concrete industry. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature and we'll get to your questions at the end. And with that, I will hand it off to you, Keith.
Well, thank you, Nick. Sorry about that. I had to unmute myself. And welcome, everyone. Good afternoon or good morning, I guess, depending on where you are. And it's exciting to be here. I appreciate the SCA providing or sponsoring this webinar and the opportunity to speak on it. As Nick mentioned, I've spent a little over 30 years in and around the concrete industry. And so I know these types of webinars are incredibly helpful. Recently, I was traveling with some friends, and a very good friend of mine said, you know, after this long, shouldn't you know everything there is to know about concrete? And as I contemplated that question, I realized, you know, there's probably very little that I actually do know. As most of you who've been around it a while realize, it's consistently a moving target. And we've got to take the material science that we have and the things that we do know and discuss these and look at concrete from kind of a large, big picture kind of view. I am in the Southeast Virginia area. So I'm in an area that's known as Hampton Roads, which includes Norfolk and Virginia Beach. And we are surrounded by water. We're surrounded by military bases. The largest naval facility in the world is about 20 minutes away in Norfolk. And so challenging concrete specifications and challenging conditions is nothing new to this area. And so, again, I thank Nick and I thank the SCA for bringing us these type of webinars so we have a forum to discuss these things. So let's jump right in. So real quickly, an overview. So today, again, we're talking about creating sulfate-resistant concrete with the use of slag cement. So I think it's important that initially we identify what sulfate attack is. We need to define it. Secondly, we'll identify some environmental risks and some internal risk in the mix, the concrete mix itself. Then we'll talk about managing that risk. What do we do on the front end to make sure that we're going to have durable concrete structures that will be sustainable and, you know, when sulfate systems are surrounding it potentially. Then we'll talk a little bit about the properties of slag cement and specifically the benefits of slag cement in mitigating that sulfate attack. And then lastly, I'll show you some examples. So for you visual learners, we'll take a look at some exposure sites where concrete samples have been intentionally exposed to sulfates, and you'll see what that breakdown looks like. A disclaimer early on, quite honestly, if we wanted to get into the weeds on this subject, we could probably present multiple webinars on just the mechanisms that are involved here. For today's purposes, this will be kind of a high-level view, kind of a very pragmatic approach. My goal would be that if this is a new subject for you, that you'll come away with a pretty good basic understanding of what's involved and how to combat it. And if it's not, if this is something that you're very familiar with, that at the very least we reinforce some of the things you do know, and that everyone would walk away at the end of this with at least another tool for the toolbox, so to speak. So what is sulfate attack? I borrowed this slide from one of my bosses. He actually presented on this topic a few years ago for the SCA. But I liked it. I kept this in place. And the definition here is sulfate attack is a term used to describe a series of chemical or physical reactions between sulfate ions and the components of hardened concrete, principally the cement paste, caused by exposure of concrete to sulfates and moisture. And while this definition is good, it really doesn't necessarily paint a picture for you. And so one of the things that I wanted to do here was kind of break this down into two subheadings. So when you talk about sulfate attack, there's really two different types, chemical sulfate attack and then physical sulfate attack. And what you're looking at here at the bottom is just a very basic kind of equation, just a sum of these things that need to be present in order for these mechanisms to take place. So for chemical sulfate attack, you need sulfate ions, you need water, you need tricalcium aluminate or C3A, you need free lime, and then you need accessibility to the paste. So basically, if these sulfate ions cannot get into the concrete structure, obviously we don't have an issue. So that's kind of a first line of defense. With physical sulfate attack, same thing. You have to have sulfate ions. You have to have water. They have to be able to be absorbed into the concrete. And then lastly, you have these periods of wetting and drying action. And I've put here at the bottom, is this oversimplification? You bet. This is absolutely a simplified version of what's going on, but I think for today's purposes, does a good job of illustrating what we're talking about. So let's break those down just a little bit more. On chemical sulfate attack, this is also referred to sometimes as classical sulfate attack. This is when sulfate reacts with the hydration product of C3A or tricalcium aluminate and free lime or calcium hydroxide. And the product that's formed with this is etranite. Now, the problem with etranite is it's expansive. And so when this starts to form, you're creating, as we all know, concrete's typically in some sort of restraint. And when you've got this restraint and now you've got expansive forces, at some point you're going to be looking at cracking, and cracking opens our concrete structure up to all sorts of nasty things that mean harm. On the physical side, physical sulfate attack, this is also sometimes referred to as salt crystallization. Now, this tends to happen in arid zones like the Western US and Canada, and basically areas with very little rainfall. And so your concrete through these dry periods will become very thirsty, so to speak. And you get this wicking action where sodium sulfates are drawn in from groundwater or soils or multiple sources. And this is followed by wetting and drying. And as this happens, you've got these crystals forming, and then they break back down into solution. They form again, reform. And same thing, you're getting expansion, you're getting stresses within the concrete matrix. And this can actually happen very quickly. We'll look at some pictures here in a minute that kind of differentiate these. So let's look at some of those sources of sulfate that might be problematic. So when you're talking about internal sources, it can come from many different things. Occasionally, at least I think it's potential. I didn't see any documented cases of this, but if you know anything about cement production, you take cement clinker. On the back end, you're at the finish mill stage, you're adding gypsum along with some other additions. And it is possible to oversulfate cement. Again, I don't know of any specific cases where this has been the case that led to later sulfate attack, but it is possible to have excess sulfates from that. Sulfate-rich aggregates, obviously. And then you can get contamination from other sources. So it may be something that you're adding to your concrete mix that in small volumes is not problematic at all, but if it's adding to an overall concentration of sulfates could potentially be problematic. Classic etranite attack that we've talked briefly about. And then I've got a special case listed here at the bottom of DEF. Now, DEF is what's called delayed etranite formation. And where you would typically see DEF is in cases where you've got very high initial curing temperatures in excess of 158 degrees Fahrenheit. So obviously mass concrete would immediately come to mind where you're generating high temperatures from hydration. Also in the precast pre-stress industry, if we've got some of you folks on today, A lot of times you're using supplemental heat to, accelerate your early strength gain, so you can get those release breaks and turn your beds over, that sort of thing. On the external side, sulfate can come from many different sources here as well. Some of those would be seawater, brackish and groundwater. Wastewater is a big one. High sulfate soils. Again, we'll kind of discuss some of those more in depth here in a minute. Examples of this would be, again, the classic etronite attack, salt crystallization. And the last of these examples I've got listed here is thomsite. Now, I'm going to give this one kind of an asterisk because thomsite occurs in some of the coldest places on the planet. And so it typically needs extended periods of cold weather is where you see this phenomenon happening. Thomsite can be incredibly destructive because it actually attacks the CSH, or the calcium silicate hydrate, which is the glue that's kind of holding our concrete matrix together. So just to look at a few pictures here. On the left, we've got an example of thomsite, and you can see just breaking the concrete down at a microscopic level here. If you look closely at that picture on the left-hand side, you can see a hand with a flat chisel. That chisel's been driven literally into the concrete. That's how soft it is there. In the top middle, an example of a chemical sulfate attack. This looks to be happening in a saltwater environment, tidal, as you can see the breakdown in the concrete structure there. Top right would be physical attack. And this is the one that, if you've traveled to the western part of the US, you may have seen before. This is where you've got high concentrations of sulfate in the soils. And that wicking action that we talked about is taking place, and it's literally breaking the concrete down from the base up. And again, this can happen very, very quickly. At the bottom, I've got listed DEF, or again, delayed etronite formation. This is on a mass concrete structure, and you can see the map cracking kind of taking place there. I've got a /ASR because there's some, depending on who you talk to in academia, you may get some differing opinions on whether ASR is a precursor to DEF. We won't get too far into that. That's a webinar for another day. So understanding the source of your sulfates and then the quantity of those in the environment is one of the first steps, obviously. Okay, what we're looking at here is on the right-hand side. This is a map of the central and western portions of the US. And as you can see, in spots like Southern California, Nevada, Arizona, you're getting really high concentrations of sulfates in the soils there. On the left, this is a chart from ACI 318. And so as you're addressing these needs, you're looking at your concrete structure that you're designing or trying to prepare a mix design for. You need to consider your exposure category. And so that would take all these things into effect: groundwater, soils, everything. An exposure category of S0 would be the lowest of these. And you can see by the chart, sulfates in the soil would be less than 0.1% by mass. In water would be less than 150 ppm or parts per million. As you move down the chart and you get to an S3 exposure, now we're talking about sulfates in the soil in excess of 2%. But I'm assured there are situations in the US where these conditions do exist. Nick, I'm getting a little note that my internet connection is unstable. So if you lose me, I'll try to get back as quick as I can.
Thanks, Keith.
All right, so one thing you'll notice here is under S1, we've got 150 to 1,500 parts per million, and then it says and seawater. So the question that you might ask would be, well, how do we know that all seawater is below that 1,500 parts per million threshold? And the short answer to that is we don't, but there is a reason for that. So When you talk about sulfate exposure class of seawater being S1, the chart on the right here, we're looking at an excerpt from ASTM C150. And in C150, there are 5 different types of cements. We'll get into this a little bit further here in a minute. But types 2 and 5 are specifically moderate sulfate resistance and high sulfate resistance. And you'll notice in the bottom of the chart there that the primary difference between these is the maximum content of CS or C3A or tricalcium aluminum, 5% on a type 5, 8% on a type 2. The reason, again, that we're looking at S1 for seawater is because we have to, again, look at the entire picture here. So when you're talking about seawater, it's not just sulfate resistance that we're talking about. One of the primary concerns when you're dealing with seawater is ingress of chlorides. So when you get chlorides to the reinforcing steel, you're dealing with all sorts of problems. So C3A at the early part of this presentation was wearing a black hat. Right now, it's actually doing some good because the C3A is going to bind some of those chlorides and slow the ingress of those chlorides to our reinforcing steel. So this is a little bit of a balancing act where, as a designer, as a specifier, you'd have to, kind of present it as a belt and suspenders model where we've got a couple things to address here. We've got multiple issues that we have to account for. And so when you design your mix, you're going to be looking at all of those things. But that's the reason for the S1 classification. Now, I'm sure there's some people on the line now that would say, well, why are you showing us charts from ASTM C150 when we're moving to type 1L cements? Or if you haven't been exposed to them already, I'm sure that's coming, or it may be that you're already at 100% on that. I want to take a brief detour from what we're talking about just to get into a little bit of that. So when you're talking about ASTM C150, the composition of Portland cement, again, we've got 1 through 5 here. And as you can see, each of those types has very specific performance or durability characteristics associated with it. And I want to look briefly at the composition of Portland cement. So the numbers you're looking at here are actually an industry average. These come from the PCA's EPD on Portland cement. And as you can see, we've got roughly 91% clinker, a little over 5% gypsum, some process addition, and then 2.7% limestone. This is in Portland cement, and again, these are industry averages. When you move on to C595 cements, which would include type 1L cement, the naming process is a little different. It's an indication of what's in there, what is blended. So for instance, a type 1S would be Portland cement and blast furnace slag cement. A 1P would be Portland and pozzolan, so on and so forth. And 1L falls under this category. And so there's really nothing in the name here that would indicate a performance characteristic or a durability characteristic. And so we have these designations. And so when you're looking at your mill report, you may see some of these, and I'll get into the naming just a little bit further here in a minute, but obviously an MS would be a moderate sulfate resistance, HS would be high sulfate resistant. So in terms of equating it to a C150 cement, if you had any of these on the left and you're combining that with a designation for an MS or an HS, then the thought would be you'd use those where you would use a type 2 or a type 5 traditionally. So let's take a look at the composition of this real quick. So this is a type 1L cement. Now we're at just under 83% clinker, 5.7% gypsum process addition, and then the target, in this case, the average limestone content of 10.8%. So I want to look at that naming practice just a hair again, and this is probably more for the producers than anyone else, is when you're looking at your mill report and you're wondering exactly what it's telling you. So these designations would be listed there where you've got, in this case, this is a type 1L with a target 10% limestone, pretty straightforward. This would be a type 1L with a target 12% limestone and moderate sulfate resistance. So logically, you could use this where you would have traditionally used a type 2 cement possibly. Testing is incredibly important, and I don't want to shortchange that. We'll get into that much more in the coming slides here. Here we've got a type 1S or a Portland cement slag blended cement with a 60% slag cement target, and then an LH designation, which would be low heat of hydration. This is similar to a C150 type 4 cement. Here we have a 1T with 10% limestone target addition, 40% target on slag, and HS designation, meaning high sulfate resistance. So when you get your mill reports and you're looking at your components, this will tell you some of the things you need to know. But again, testing is critical here. So we're understanding the vulnerabilities of the concrete mixture to sulfate attack. So now we have to utilize the established guidelines and or laboratory evaluation when we're considering what constituents we're going to use and what that mix design is going to look like. So the primary test for evaluating cement and SCMs for this is ASTM C1012. You may or may not be familiar with this, but it's a lengthy test, and it's used to evaluate sulfate exposures and the corresponding expansion of combinations of Portland and blended cements, pozzolans, and slag cements. So this is a mortar bar test, and it's got fixed water cement ratios. So if it's an air and train mix, we're going to use 0.46. For a non-air and train concrete, we'd use a 0.485. And these mortar bars are stored in a sodium sulfate solution, and they're measured for length change over time. The earliest test being at 6 months, going all the way out to a year and a half. And I like the picture that's shown up there. You can see the cracking starting to take place in the animation there as it's soaked in that sulfate solution. This is a chart from ACI 318 again, and I believe there is an updated chart or series of charts from this. I would encourage you to take a look at that yourself. Unfortunately, when I went to my digital copies of this, I wasn't able to access what I needed, but I think for purposes today, this will cover what we're talking about. So again, let's break it down. We're looking at an environment where we know we have sulfates or potentially have sulfates. We need to address what exposure class that is. And so on the left-hand side, you see we're ranging again from S0 through S3. And then as we move to the right from there, we're going to have some options. Water cement ratio, strength and PSI, the cementing materials that would be used, and then all of those things in combination with performance requirements. So for an S0, basically, as you can see, there's no requirements. So that's saying that we're not susceptible to sulfate attack here. There's really no special recommendations that are made. As you move down the chart, you will see obviously water cement ratio lowering, strengths a little bit higher, different cementing materials used. Let's move all the way down to an S3 designation for just a minute. So here we've got two options. At a 0.45 water cement ratio and 4,500 PSI, basically the only acceptance criteria is performance. So in this case, we would need, from C1012, we would need results of less than 0.05% expansion at 12 months and 0.1% expansion at 18 months. If you want to drop that down to a 0.40 water cement ratio and a 5,000 PSI 28-day strength, it's recommending a type 5 or a C595 cement with an HS designation. And you still have to meet performance requirements of 0.05% at 6 months and then 0.1% at 12 months. So this is where we're kind of getting our guidelines and protection in terms of addressing the sulfate mitigation, sulfate attack mitigation. And I think it's really important to address here that well, I can't speak for the industry as a whole. I know that for us, our company, we do internal C1012 testing. We do it with all of our cements, and we use multiple different SCMs, so that information is typically available. I would imagine others are very much alike, but I would encourage any concrete producers to address this on their own with their materials. The test does take a long time, and I understand that's problematic in some cases when you get these specifications. Maybe you haven't seen them before, but this information is typically available, and it's really important to understand. So just a quick summary and talking about managing the risk of sulfate attack. So some of those preventative measures are this. We are reducing the cement C3A content. We can do this utilizing a C150 type 2 or type 5, or a C595 cement with an MS or an HS designation. We're reducing that C3A available. Reduction of paste permeability. This is super, super important. So anytime you lower the water cement ratio, obviously you're reducing permeability in your concrete, and you're making it harder for those deleterious materials to reach the paste. SCMs, adequate curing. This is one that gets overlooked a lot, but adequate curing can greatly reduce the ability of sulfates to penetrate into concrete. And then use of SCMs at suitable replacements. Slag cement, obviously, Class F fly ash, silica fume, all of those contribute to reduction of overall C3A and permeability, with the added benefit that all of those particular SCMs will utilize excess free lime in your concrete mix and produce additional CSH, or calcium silicate hydrate. Again, that's the good stuff that we want more of, reducing permeability and giving us incredibly durable concrete. So you might say, well, obviously, if I introduce SCMs, then I'm covered, right? Well, not quite so fast. The picture you're looking at here is mortar bars that were made with a very high C3A cement. So this might be a traditional type 1 with, say, an 11 or 12% C3A content, and then a 40% high calcium oxide fly ash. And this is after 2 years in a 5% sodium sulfate solution. And you can see the devastation here to the mortar bars. So knowing your materials is critical here, understanding how they work together, and having those C1012 results are really important as you start to address these things. The C3A contents and everything that we've gone over before are rules of thumb, but I don't think anything can be a substitute for testing when it comes to this. So we talked about water cement ratio already, and the benefits of that and sulfate attack resistance. The pictures here that you're looking at were both produced, these beams were both produced with concrete that had a type 5 cement. The difference being that the one on the left has a water cement ratio of 0.65, on the right, 0.38. And these samples that we're looking at are after 12 years being exposed to a sodium sulfate solution. And so I don't know anywhere or anyone that would look to put a 0.65 water cement ratio in structural concrete. It'd be a rarity, but this does a good job of showing you the disparity between those two and what the effect of water cement ratio is on that reduction of permeability and permeability's role, conversely, in mitigating sulfate attack. So one more time on delayed etronite formation. Again, the special case of internal sulfate attack, and with initial curing temperatures over 158 degrees. This late age etronite can cause expansion and cracking and break down your concrete from the inside out. If you look at the photograph on the right, this microscopic view, the large gray particles there are obviously aggregates. And then in between, you're looking at the ITZ, or the interfacial transition zone. This is where your paste is tying into your aggregates there. And as you can see, where the E is at the bottom in the green arrow, you've got etronite forming, and it's pushing against that paste off of the aggregates, kind of creating volume in that space. And as you can see, the cracking already taking place, breaking that concrete down from the inside out. So just a honorable mention here when it comes to delayed etronite formation. If sufficient SCMs are used, and the right SCMs, early age temperatures up to 185 degrees Fahrenheit are acceptable according to ACI 201.2. And so we'll get into this in a minute as we talk about slag cement, but there are some ways to combat that delayed etronite formation. Okay, so let's talk about slag cement for a minute. And I would imagine that most everyone on here is familiar with slag cement, but if you are not, slag cement is I think I moved ahead, didn't I? Yep, sorry about that. So slag cement in its finished stages is a fine white powder that can be used as an SCM to enhance properties of concrete. In the presence of moisture, it will exhibit hydraulic properties. So if you mix it with water, it will set up, it will harden, it will gain strength. Where does it come from? So steel production, you need an iron ore blast furnace. And basically you've got the molten iron ore, and then you've got a waste stream of this slag, which is the waste product. And so as this is diverted, that waste product is quenched, and then it becomes this glassy granular product. That's not the end of the process, but that's what we start with. So you've got these granules, and as you're looking to your left there, you see the granules. They're ground to a suitable fineness. And you might ask, what is a suitable fineness? Well, it's typically finer than Portland cement. And this can be used in concrete mixtures to enhance durability and sustainability. Does all sorts of good things in your concrete mix. Topic view of the finished slag cement. As you can see, the particles are angular in shape. And then on the right is a slag cement grinding facility. This is a ball mill. So when you talk about slag cement reaction and what it's doing within your concrete system, I think this slide does a great job of illustrating that. So on the left-hand side, we're dealing with a Portland cement concrete system. On the right, we're looking at a Portland slag cement concrete system. So the aggregates are obvious there in the brown. The Portland cement is the gray particles here, slag cement particles being the white, and then the CSH is the yellowish that you're seeing there. In between, you've got your voids and free lime. And so as you can see from this illustration, one thing that's happening here is with slag, you get the benefit of some particle packing. And so there's densification on a physical level from just that particle packing. But you're also getting the benefit of some of that free lime that we're looking at on the left-hand side being tied up, being reactive with the slag. And now we're creating additional CSH, or calcium silicate hydrate. And that's what we want. We want more of that. And so as you can see very clearly, the system on the right, fewer voids, much denser system, lower permeability. Anytime we lower the permeability on our concrete, we're going to have enhanced durability. So we'll talk about permeability for just a second, and a little bit of testing involved with that. So permeability is basically the measure of how easy it is for water, air, and other substances to enter concrete. Standard tests for this, or one of them is that you see quite a bit, and I'm sure a lot of you are familiar with ASTM C1202 or rapid chloride permeability testing. What you're looking at in the picture on the right is basically a 2-inch wide slice of a 4x8 cylinder. We won't get too much into how it's prepared, but basically you've got a sodium chloride solution on one side, sodium hydroxide solution on the other, and you're running a current through this. And then we're going to measure charge in coulombs. And so the lower the coulomb values from this test, then there's a direct correlation with the permeability of our concrete here. We're actually doing a job here in Norfolk, the Hampton Roads Bridge Tunnel, which has about 600,000 cubic yards of concrete in it. And they're running C1202 testing every 100 yards. So every time they make a set of cylinders on this project, they're running this test, which that's a rarity for anyone who's familiar with the test. But it's given us some pretty valuable information to look at. So why is that important? Obviously, again, lower permeability concrete reduces corrosion potential and we don't want that reaching the reinforcing steel. So how does slag cement help us when it comes to permeability? When we looked at the previous slide, we talked about slag cement reacting with the free lime or the calcium hydroxide, creating more CSH and reducing the permeability. And low permeability can be achieved in binary and ternary systems with 25 to 65% replacement rates. There are some notes in ACI that kind of deal with this, but I think the reason this is important is slag does a number of good things, but this lowering of permeability in these concrete systems is really the primary focus and the reason it aids the durability of our concrete so much. So looking at this chart here, what we've got is this is C1012 testing. Line there is OPC or ordinary Portland cement concrete system. As you can see from the expansion levels at 180 days, and sorry, the vertical axis is the expansion percentage, and then the horizontal axis is the age in days. At 180 days, we are still below that 0.1% expansion threshold, which would mean this cement would meet an MS designation, or if it's ordinary Portland cement in this case, would be probably a type 2. But as you can see, with as little as 25% slag replacement, we're looking at expansion levels below 0.05% expansion well past a year. So we're getting great permeability reduction and resistance to sulfate here with the use of slag cement. This test was kind of specifically designed to address delayed etronite formation. So in this case, we used a type 3 cement, or a type 3 cement was used with differing replacements of slag from 25% to 50%. And then it was cured at 203 degrees Fahrenheit initially, and then it was stored in water for 2.5 years. Deleterious expansion for this is being defined as 0.1%. And so you can see the ordinary Portland cement curve there, and then everything else, 25% through 50%. DEF was basically eliminated through the use of slag cement here. So that's pretty powerful evidence there. ACI 233, these two here are basically taken into account. On the left, we're looking at a type 1 cement with a pretty high C3A content, looking at 11.8%. And as you can see to the far left there, the curve almost straight vertical, where we are very susceptible to sulfate attack. But with as little as 40% slag, we're still below the proposed equivalents for a type 5 cement. If you look at the asterisks there at 0.1%, the proposed ASTM C1012 limit. So all of the slag replacement levels fall well below that. If you look at the horizontal axis here, we're actually looking in years. And so you see very good results heading out 2 and 3 years there, even with only a 40% slag substitution. On the right, we're looking at a type 2 cement. So we had a moderate sulfate resistant cement here we're using. And then we have slag cement at 40, 50, and 65% substitutions. And again, you can see the dramatic difference when we get out to a year with the slag substitution and how that affects our permeability and sulfate resistance. This again, just kind of showing you rules of thumb for if, let's assume for a second that you're in an area that has high concentrations of sulfate in the soils or in the groundwater, but you're limited in the cements that you can purchase. Let's just say you've got a type 1 cement with a high C3A content, and you still need to have some level of sulfate resistance here. This is just guidelines. Basically, if you want a type 2 equivalence, you'd need to add 25 to 50% slag. Type 5, that would bump up to 35 to 65%, and so forth and so on. So I did want to show you some examples here of exposure sites. And so this one is from Toronto, 2010. There was an 8-foot deep trench, basically, where these samples were going to be kept. Variable annual temperature between 37 and 61 degrees Fahrenheit. And then they were put in a sodium sulfate concentration of 15,000 parts per million. Several different combinations of mixtures were used. The first being a type 1L, with 10.5% target limestone. The C3A content on the type 1L was at 11%. And then they used a type 5 without any SCMs at a 0.40 water cement ratio. So this is from 33 months later. And as you can see, most all of these had minor damage, including the type 1L with 40% slag, fell in line with the type 5 cement. But just bumping it up to 50% slag under these conditions, and we've got excellent condition on all of these samples. So finding that right concentration of slag cement, you get great benefit from even a little, but understanding where those guidelines are and having that testing in hand will give you a great indication of what you need to use to manage any potential sulfate attack. Now, how about 38 years of sulfate exposure? This is kind of crazy to me, these slides, but moving from the bottom to the top, in the bottom, we use just a moderate sulfate cement, a type 2. All right, so what was the last thing that you heard? All right, we'll just start over again on this. So again, moderate sulfate resistant cement used on the bottom 2, high sulfate resistant cement used on the middle 2, and then at the top we've got a general use cement, but we're using a 65% slag replacement. And you can see after 38 years of exposure, just how much resistance to that sulfate attack that the slag gave us in this case. And so I believe that is the last slide that I've got, and I will open it up to questions.
Perfect. Thank you, Keith. I do see we have one question from Maria, and she asks, is there a concern with slag cement availability in the future and the potential of it being phased out due to the use of electric arc furnaces?
Well, you might even be in a better position to answer that question than me, Nick. I honestly don't know the future of that. I don't see that happening right away. There seems to be slag granules available in other places. There's quite a few that are being imported here and to grinding facilities, or imported slags being brought over. But at this point, I don't know that that's going to happen in the near future, but certainly remains to be seen.
We received another question. Do you expect any significant differences in some of your sulfate exposure test results using type 1 versus type 1L? at higher replacement percentage?
That has not been our experience, and we've been testing type 1L and type 1-2 cements with C1012 testing for several years now. And what we found is the results are very, very comparable. I know that PCA did a lot of testing as well and saw similar results. As it stands right now, the information, the data that we've seen has consistently been very, very similar.
We have another question says, what extra curing requirements are required with slag cements?
I think good concreting practices, no matter what your concrete mix design looks like. So wet curing for, 7 days, something along those lines, where you've got soakers and plastic, or, there are any number of remedial things that you could be doing, but just good concrete practices in general.
Perfect. Those seems to be the questions that we have so far.
Okay, and if anyone else has some, feel free to share my information so that they can reach out. I'd be happy to address them. If I can't answer them directly, we'll certainly get them an answer.
Yes, and if you have any questions, you can email us at info@slagcement.org. We get all your questions there. I think we can move on to the last slide now.
Okay.
All right. Before we go, I just want to let everyone know about an upcoming SCA event, Slag Cement School. Slag Cement School will be held in Cape Canaveral, Florida on May 22nd to the 23rd. The school will include educational presentations on slag cement use in concrete construction, sustainable resources available, and other presentations on benefits of use. On day 2, attendees will get a behind-the-scenes look at a local cement plant. You can learn more about the event and register at slagcement.org/school. I hope to see you all there, and thanks again for attending this webinar.